All right, folks. So last time we talked about trees or decision trees. Decision trees were the first algorithm that were, I would say, in the class of nonlinear algorithms. Before that, all the things that we learned so far in ML100 and in the previous lectures would draw a linear decision boundary. We would draw either a straight line to fit the data, or we would draw a straight line to bifurcate feature space into two halves, or maybe three halves or four halves, partition it into multiple halves, using logistic regression, linear discriminant analysis, quadratic discriminant analysis, and so forth. I mean, and this is only true for those of you who attended the previous workshop. But the bottom line is, if you didn't, the bottom line is, we would take the feature space and we would partition it into components or pieces or subregions using linear decision boundaries, or linear hyperplanes as the decision boundary. Decision tree, on the other hand, was the first algorithm we encountered where you could make all sorts of complicated decision boundary. Ensembles I talked about as the wisdom of crowds. There is actually a theorem in mathematics that was discovered a long time ago. It says that if somebody's chance of guessing an answer is just a little bit more than 50%, right? So in other words, the person is a weak learner, or just about slightly gets it more right than wrong. Then in a systematic way, you can harness the wisdom of crowds. You can take a lot of these weak learners and, excuse me, you can create an ensemble, a crowd of these. Then you can aggregate their wisdom. How do you aggregate it? If you are doing regression, so suppose you want to ask people, like I did, like I told you, I used to do that in class. When we used to physically meet in the before COVID world, I would give you guys a jar of stones and ask you to guess how many stones are there. Invariably, almost everybody would be wrong. Maybe one or two people will be close to the right answer, but the average of those answers was uncannily close to the right answer. The reason for that is all of us have a bias. We have certain information in our decision and certain bias, right? So we may guess either optimistically or pessimistically. But then as you add up everybody's answers and average it, the average of the errors cancel out. But the average of the information remains the information. And so the right answer begins to stand out. That is the wisdom of crowds. Now, why weak learners? I talked about this thing that weak learners are better than strong learners. It turns out that strong learners have a higher tendency to get correlated with each other, entangled with each other in their decision making. So in other words, they begin to think alike. When two learners are thinking alike, they are redundant. You can just use one rather than two, right? So for example, if you need to get an understanding of whether there's global warming or not, the last thing you want to do is get two members from the same think tank, right? Because all the members in the think tank have been looking at the same data and coming to the same conclusions. So either both of them will strongly favor the statement that human beings are causing global warming, or both of them will strongly favor the statement that, that human beings are simply not the cause of global warming, it's natural cycle of the earth. You see my point, right? So if you really want the wisdom, or you want the truth to emerge, you want to take intelligent people who are making, but not necessarily pundits. You want to take just intelligent people who are capable of thinking on their own. Enough, just more than 50% right or sense in them. And then you take a collection of them and you'll be surprised at how uncannily right they are generally. Right? So the basic ideas are you need weak learners, you need a lot of them, and then comes the other aspect of it. See, what happens is if all of them are reading the same book, they'll reach the same conclusion. So the way you ensure that the learners don't get correlated or entangled is in their learning is by giving them different windows into the data. So one metaphor that you can use is blind men and the elephant. So you have a big elephant of a data, but to each blind person, you blindfold them. And so each person gets to see and feel only a part, or rather feel only a part of the elephant. So one feels the trunk, one feels the ears, one feels the tummy, one feels the legs, and so forth. But if all of them are willing to agree that they are all correct, the picture of the elephant will emerge, isn't it? Or more prosaically, see, whenever you take a picture, a photograph is a two-dimensional representation of a three-dimensional thing. You take enough photographs of a thing, you will be able to reconstruct it in its full three-dimensionality, so long as all the photographers are not taking photographs from exactly the same vantage point. If they are all taking pictures from the same vantage point, you would really not know what is out there on the other side, right? Or on any side except the front from which they're taking the picture. So for them to collectively be able to reproduce the building in all its three-dimensionality, you need to take an ensemble of those photographs from different vantage points, seeing different realities, subset of realities. See, when you look at a building, you don't see the whole building. You see a subset of the building, the part facing you. And that is very similar to what you want to do. You want to give each learner only a subset of the features. So suppose there are 10 features there, you want to pick a small number of features, 2 or 3, and give it to them. So the way, if you remember, I motivated it was with the story of, or the metaphor of a teacher taking a bunch of school children to a special zoo or a meadow. In that meadow, there are only 2 animals, cows and ducks, right? Now, the teacher being highly scholastic, she begins to explain in intricate detail what are ducks and what are cows. So she talks about the fact that cows are big compared to ducks, that they have a swishy tail and big horns, right? And they have 4 legs and hoofs, and so forth. On the other hand, when she talks about the ducks, she emphasizes that they're small, feathery, webbed-feeted, beaked, right? Winged creatures. So you may speak a lot about the attributes of a duck and the attributes of a cow. Imagine that these children are all pre-kindergarten children, right? Or preschool children. You have taken them and you're explaining so much. What will happen is different kids will latch on to different attributes. One may remember, for example, that if it is big, it must be a cow. If it is a duck, it must be small. And she may also remember that if she sees a tail, it is probably a cow, right? Things like that. If there is no tail, then it's probably a duck. Some other child may latch on to the fact that webbed feet is it. Look at the feet. Are they webbed or are they hoofed? If you see hoof, it's a cow. If you see webbed feet, it's a duck, right? Or she may notice that there are beaks. Is there a beak? If there is no beak, it's not a duck. So different kids in that crowd of collection or a class of kids would latch on to different pieces. Being little children, they're not going to understand all the anatomical differences that the teacher pointed out. And so now the teacher shows an animal and asks, what is it? Let us say that the animal is at a distance. Then to the kid who's looking for size, that cow may look rather small and may confuse it to be a duck, right? But let's say that the duck is flying around. The other child may happen to notice that it's a winged creature. It flies occasionally. And so it may come to the conclusion that it's a duck. So all of these children, they will come to their own conclusion between cow and duck using what they have learned, right? They're looking at different subsets of the reality. But collectively, if you take the majority vote, you ask those children, what is it, cow or duck? Let's take the majority. Whatever it stands for, the majority stands for, you will notice that time and time again, that will be uncannily close to the right answer, right? And very infrequently, they will be wrong, whereas each child would individually be often wrong. And that is the point of of ensembles. The other point, so that is your point C here. The point D is not only should you let them look at different aspects of the reality, you should also let them see or learn from different samples of the data. Right? Because the data may have, any data sample may have some peculiarities. So just by accident, it may so happen that overall the majority of the animals are white in color or something like that, or brown in color, right? And so you might begin to draw conclusions like brown things are, or brown things are cows and ducks and so forth, and ducks are not brown and so forth. But that may not be really true. So if you give subsets of the data, you sort of protect against an overall bias of the data. Right? So that's the point of giving different subsets of the data to different learners to learn from. So all of these things put together, those are our main 4 points. A, you need weak learners. You need many of them. You need different learners looking at different aspects of the subsets of the features. And D, you give them different samples of the data. Right? At the end of it, you want to make sure that the learners are not correlated. If they are correlated, then the bully feature becomes important. Right? So suppose there is one feature that always misguides. You see, the problem with decision trees has always been that if there is one, if you make your first split wrong, you get completely screwed thereafter. It's a fatal decision. The rest of the tree takes you down the wrong path. So, but then the root bifurcation that you do, you based it by scanning all of these axes. Let us say that one of the feature is dominant, and for whatever reason it misleads, because either the data is wrong or biased, or whatever reason, and that feature always misleads. So what will happen? Your decision tree will always come out wrong. But if you create lots of decision trees, like let's take the example of decision trees. Those learners can be decision trees, but they can be anything else. Suppose you take a lot of decision trees, but to each tree you only give a few of the features. So what will happen is the majority of the trees will not get that dominant feature that is screwing up the analysis. So some trees will make a mistake because they got that feature. Majority of them won't. So I'll illustrate it with a number and an example. Suppose there are 100 features. It is a good idea never to give more than square root of the total features. Here, the total features are 100. What is the square root of 100? 10. So to each tree, you give no more than 10 features. So let us say that there is a bully feature and you create a few hundred trees. By the law of large numbers, it will happen that only 10% of the trees, 1/10 of the trees will get that bully feature. So 1/10 of the trees will get the answer wrong quite often, right? But then that's the beauty of it, because you're ensembling before you're aggregating the results of the ensemble. 90% of the trees will come back and give you the right answer. And so the bully feature gets muted, it gets suppressed, it gets neutralized. Do you see the point, guys? Huh? So that is it. Now, how do you take the aggregate? It's very simple. If you're doing classification, as we talked, you take the majority. If you're doing regression, you take the average of what they're saying. So you ask the children, like for example, I would ask you guys, how many stones are there in that jar? Whatever number you say, we take the average. You want to know what's the temperature outside? You ask all the children, what do you think is the temperature outside? And then you take the average value, and that's your prediction of temperature outside. Are we together? Right? So that summarizes what we have talked so far. Guys, please stop me here if you have not understood so far. Are we good so far, guys?
Good.
Magesh, did you follow any part of it so far? This must all be looking a bit strange.
Yes, Asif. Yeah, getting it.
You're getting it, huh? Very good. Anybody else has a question, please ask me. Otherwise, let's take, it's 8:30 now. Should we take a 15 minutes break and regroup at 8:45? Let's go sip some water and so forth. And let's get together at 8:45.
Asif, I just wanted to ask you, when you said, we need a mechanism to keep the bullies who can dominate neutralized,
Yes,
is that the way we like when you gave only a part of the features to each
yes,
decision tree? So
exactly.
is that achieved by that?
Exactly. In fact, the rule is square root. If you have
Okay.
p features,
Mm-hmm.
never give more than square root of p. In fact, that is one of the mathematical theorems. It's a theorem about data projections.
Okay.
You just need square root of p at most features to get, there are words like, isometric embedding and so on and so forth. I wouldn't go into the mathematics, but take it as a fact that it works,
Okay.
right?
Thank you.
Behind all of this, I've given you the intuition, the gut feel, or the picture. Uh, each of these are deep wells of knowledge, mathematical knowledge. So you can keep drilling deeper and deeper into it. It's a big rabbit hole.
Okay.
Asif?
Go ahead, Mridul.
Just want to make sure, just my understanding. This Gini index is giving like the proportionality, right? Of when it derives from there.
It's derived from
This
proportionality. Both
yeah.
entropy and Gini are derived from proportionality.
And ROC curves are also derived from proportionality, right? That true false.
ROC curve is different. No, it's about model metrics.
Okay.
It is about the precision and accuracy, or rather, a false positive versus true positive.
Okay.
So, in other words, as an aside here, ROC curve is, suppose you take a certain cutoff in the data, like, see, suppose you have a probability that it's a cow.
Mm-hmm.
Suppose you can say cutoff is half. If it is 50% probable, mark it as cow. Or you could have taken 1/4. Even if it is 1/4 probable, that's a cow, it's a cow. Or maybe you need a lot more assurance, 3/4. So you can, the probability X where you put the cutoff determines the rate of false positive and true positive.
Okay.
Right. So if you're not careful, see, a bad model, right, that is making random guess will have equal rate of true and false positive.
Yes.
Because it's clueless, right? But a good model will achieve very low, right? For a very low false positive rate, it would have already achieved a very high true positive rate, which makes sense, right? You want a good model that is a high true positive rate for a very low false positive rate. So this is the ROC curve.
Right. So if like after partitioning, if Gini index gets better, the ROC will get better, right?
Oh yes, of course.
Yeah. That's how they're connected, right?
Yeah, they are, in that sense, yes, they are interconnected.
Yes, whatever.
Yes, so yeah, that's a good point. Suppose so this is your square box, right? This is a pretty bad baseline. You can actually do worse than baseline, but let's say that in your first split, you're getting an ROC like this. Then the second one will give you an ROC, like a better ROC. A third one will give you ROC like this, and a fourth one will give you ROC like this, and hopefully a very good model will eventually give you ROC like this. So let me mark it 0. So let me call it the first split 1, 2, after the third.
Okay. Impurities keep getting better and better, right?
Yeah, exactly.
Genies keep getting better and better. Yeah. Okay, that's the intuition.
Fire keeps improving. Right?
Thanks a lot. Yeah.
So this is your ROC curve. So this is a good observation, actually.
Yeah. Yeah. I just want to make sure. Thanks a lot.
This is. And
True system.
all right, guys. If we are clear, it is already 8:36. So let's make it 8:50. Let's meet in 15 minutes. Huh? And I'll pause the recording for now. And we will restart the recording. So if you guys want to talk without worrying about being recorded, this would be hit Control Shift Alt H. Pause. Where am I? So we'll talk about the concepts of bagging and boosting. These are two important topics, right? So we'll talk about this, except that today we'll limit ourselves to bagging. Right? This word bagging is actually a combination, or the, what's the word, portmanteau of two words, bootstrapping.
Compound.
Say that, Kate, again.
Compound.
Compound, yes. Bootstrapping and aggregation. Well, it's an often interview question that people ask, what is bagging? See, usually people don't know, and sometimes even interviewers don't know. They just talk about the mechanics of it, but it is actually the compound of these two words, bagging, bootstrapping, B-A-G. Do you see that? Bag. So what is bagging and what is bootstrapping? One way to, let's talk about bootstrapping. What is bootstrapping? Bootstrapping is, and I'll give you a very rough idea. I won't go into the formal definition at this moment. So suppose you have points, data points. Let me mark these data points with a certain color. What color would suit us? Let's go with this color this time. So suppose you have a data points like this. And this is the sum total of your data points. And you want to generate training data out of this and give it to one of your learners, right? So I told you that don't give the same data to each of the learners, right? What you should instead do is pick a different subset for each, pick a different subset of data. So for example, to one, you can give this data. To another, you can give this data. To another, you can give this data. To another, you can give this data. Do you see that? Right? And you realize that different people, different sets, different samples, let me call it I, J, K, L, M. So sample I and sample, any two sample given I, J, sample I intersection sample J is not necessarily null. In other words, samples may have overlapping elements. Are we together? And you obviously take random samples. So this process is bootstrapping. Are we together? This is bootstrapping. And I'm giving you just the whole flavor of the whole thing at this moment. Let's go with that. So far, so good. And nature of bootstrapping is, some people will say, you take a sample and then you replace it back into the bag. And then it's like, you know, if you have peanuts in a jar, you put your hand in the jar, you shuffle and you take some peanuts out, look at it, and then you don't eat it up, you put it back, so that the next time you again put your hand in the jar and you take another bunch of peanuts out, and some may have belonged to the first time you took the peanuts out. So that is bootstrapping, roughly speaking. Then there is aggregation. Aggregation is much simpler to understand. Aggregation. Aggregation is, simply put, just for regression, take the average prediction from each learner, and for classification, by the way, guys, is my handwriting reasonably legible? Are you able to read it? Or it's still
Yes.
Yeah. It's okay.
And for classification, take the majority. So for example, if you have vote of the learners. So for example, if the learners are little children that you have taken to the meadow, you look at an animal and you ask each child, is it a cow or a duck? And now look for the majority answer, right? And let us hope that you took an odd number of children, so you always get a clear majority. In the same way, if you're taking regression, so suppose you're asking them, for example, for the temperature, whatever their prediction of temperature is, and the temperature is, one child will say it's 72 degrees, another will say, no, it's 60 degrees, another will say it's 80 degrees, and you're asking them to predict the weather as it would be, let's say 1 hour later, right? So they will all make their predictions, take the average of the predictions, and the average is the correct answer, is the answer that you use. You say that it is the answer of the ensemble or of the crowd. The crowd has answered, and the crowd says the temperature is likely to be 80 degrees. Right? So do we understand aggregation also now? Right. So these two put together makes bootstrapping. Sorry, not bagging. Bagging is bootstrapping plus aggregation. Did we get that? Now, that is bagging. Boosting I'll keep for the next time, but let me mention a very popular algorithm that uses bagging. It is called, can somebody tell me what it is called?
RandomForest.
RandomForest. And its close cousin, which is slight improvement, but somewhat lesser known. There are many variants of it. For example, there is extremely randomized trees, etc. But let's go with RandomForest. So what are RandomForest? RandomForest is, the criteria is the learners are the trees. Right? B, take lots of them. Take or create lots of learners. My basic rule is I start out at greater than 100 and I go up to typically, based on that situation, 400 or sometimes 1,000. Like lots and lots of learners. We live in the world of computational plenty. Go at it. Huh? The second thing is, see, to each learner, give a bootstrap sample of the training data. Don't give it the whole data, give it a bootstrap sample of the training data. By now, can I assume we understand the word bootstrapped sample? Just to remind you, this is it. This red thing here is the bootstrap sample. Randomly go pick a small sample of the data. Right? The next thing is, not only that, right? Let the feature space be RD, i.e. R, not D, let me make it P. Suppose there are P features. P. There be P features. P can be 5 or 10 or whatever, 100 features. P features. Let the feature space be then give to each learner only a subset, let me call it S, which is much smaller than, obviously, than equal to P of the features. So you can give it, all the features to the, of the features, but ideally, less than P features. That, you see, the random forest algorithm doesn't put a restriction, but math says, right? And I won't go into the math, there's a whole random projection theorem, but I'll just leave it as a more intuitive word. Just say that the wisdom of math says, S should be less than actually the square root of P. So I'll just leave it S of the features. The math says, yeah, S of course, maybe so P of the features, but actually you should not take. So for example, if there are 100 features, what is the square root of 100? 10. So take only 10 of the features. That's it. And then you build the model, and then the last thing is aggregate the results. Let each of the models be trained. Let each of the learners learn in parallel to build a model, to each build their decision tree models right? Then for inference, let each tree learner make its own independent prediction, make its own prediction y hat, right? So each of them will make their own independent prediction, right? So let's say that the learner is L, and you're making a prediction on the data set I. They will all make their own prediction, right? And the last step is aggregate the predictions to get an overall prediction. So this is a sequence of things, What have we done in random forest? Let's look through the steps. We are saying you take so you need to pick some learner. In random forest, you use trees, which explains the word forest. What do you call a whole bunch of trees growing next to each other? You call it a forest, right? Now, I'll explain the word random in a moment. So now you create a lot of trees. Obviously, for it to look like a legitimate forest, you better have a lot of trees. More prosically, you need a lot of learners. So you need an ensemble. So this is your ensemble piece. Once you have the ensemble, now what happens? To each ensemble, you need to give it data. Each tree, you need to give it data to learn. Give it a bootstrap sample. Don't give the entire training data to the tree. Once you have done that, now what you do is, even from that sample, you don't give all the features. You take a random projection of the features. Right? So the word random comes from that, a random subspace. Random is a random subspace of the data. Subspace or projection. So the random in random forest is not that you take a random sample. That would be bootstrapping. It is the random projection that you do, or the random subspace that you pick up of the feature space. Huh? That's what you do. And so do you notice that these words, they sound rather formal when they're written in textbooks, but they actually have a very simple interpretation. Now, all of these learners, there's no reason they need to wait on each other. So they can all learn in parallel. In fact, they better learn in parallel. The more unaware each is of the other, the better. You don't want them to get correlated. And finally, you draw an inference. Let each tree, so suppose you want to make a prediction on a data. You show it an animal. Let each of the tree tell, is it a cow or a duck? And then you take the majority. Or if you ask the tree to tell what temperature is going to be tomorrow at noon, let each of the trees make an inference, and then you take the average prediction. So that is the aggregation part. So you notice, guys, that we had to put a lot of ducks in a row. Right? We took the idea of ensembles, we took the idea of random projection, we took the idea of bootstrapping, and we took the idea of aggregating. So we had to put 4 ducks in a row to get this algorithm, random forest. It is a beginning of what our world is going to be going forward. If you have done ML100, and so far you have been dealing with simple algorithms based on one idea. Right? Random forest is your introduction to a complex algorithm where you have to put many good ducks in a row to get a good algorithm. You know, many ideas come together, or strands of thinking come together to form the big picture, the big idea, or the full algorithm. It has many good components to it. Random forest, the limitation of random forest is, it is a black box model. If you ask a random forest, why are you making those predictions? It will just shrug its shoulder and say, well, I like to make that. That's what I learned. Now, what exactly did you learn? It won't be able to tell. It's a black box model, right? All you get is the X vector goes in as input, and Y hat, Xi goes in, and Y hat comes out as a prediction. Are we together? You can't open this box and ask, what is there? How is it making the prediction? Explain it to me, right? It is not a model that has a parameter. That's why I say it's a non-parametric model, right? It's too hard. You cannot say that there is beta naught, beta 1, beta 2, and so on and so forth. And so these are the knobs I can use to explain to the user why the machine made that prediction. It's quite a loss to be able to lose interpretability. So it degrades into. So interpretability is a big sacrifice you make. Sorry, I pulled that word. Interpretability, sacrifice. Quite a bit, but not completely. There is one silver lining. So we better take a silver colored pencil, I suppose, for silver lining. Is the silver colored? Looks like it. Silver lining. I'm joking, guys. Huh? Silver lining. So there we go. We have a silver lining. Silver lining is one thing that you have in linear models or straightforward models is interpretability. You can compare the size of the coefficients and get some sense of how relatively important each feature is. That is preserved. Feature importance the relative importance of features. Rough global average level is preserved. Now, I used a lot of words. Let me explain it. Rough global average level is preserved. But forget the rough global average word for a moment. It will tell you that suppose you're talking about diabetes, and let's say weight is a factor, age is a factor, right? And weight or size of the person. And maybe the two put together make a BMI, but let's skip that. And your age and your and a few other factors, genetics, and so on and so forth. And you're trying to determine, given all those factors, is the person likely to be at risk of diabetes or not? At risk of diabetes. And when you build a model, let's say that you successfully build a model in which Xi goes in, and you predict at risk, true, false. Then this model, this random forest that you have, you can ask it that in making the decisions, how important were each of these factors, each of these effective contributory factors, weight, age, size, etc. So it might come back and say that, hey, you know what, let's say weight matters most. Weight matters most, and then is greater than age. Let's just say, I'm just putting, I don't know, a doctor may disagree. So size, genetics, I don't know what the right order globally would be, something like that. But there is a problem with this. Random forest gives you that. The trouble with this is that it gives you sort of an averaged out feature importance. That on the whole, this is what it is. It doesn't capture the nuances of prediction. So for example, when in different regions of the feature space, for example, this region of the young people, what happened? A lot of background sound. If you can please mute yourself. Okay, so suppose you're looking at the young people here, then for the young, as you know, unless you have type 1 diabetes, so let me just make it type 2, adult onset type 2 diabetes. Unless so children tend not to have type 2 diabetes, right? Even if they are relatively overweight, they tend not to have type 2 diabetes unless there's a genetic predisposition to it, right? So you might say that for young, genetic factor is here, genetics is overwhelming, is more important. But as a general population, you may agree that for people who are older, over 40, greater than 45, now suddenly what begins to matter? Weight and size, of course, together making up the BMI matters. And let me throw in exercise here. Exercise matters. Exercise matters. Things like that, they begin to matter much more. Right? I don't know. Medically, I'm quite likely to be off, but I'm just using this to illustrate a point that in different regions of the feature space, or for different age groups or different weight groups. So, for example, if you take all people over 45 and the same BMI, now all of a sudden genetics will begin to matter a lot, or the level of exercise will begin to matter a lot. So, feature importance is actually a very complex and nuanced topic. And it is almost very poorly understood by most people doing data science. They don't understand the sheer complexity and nuances of feature importance. So anyway, I'll stop today with the statement that whenever you talk about feature importance, and even when you read these books by all these publishers, they actually they can be quite misleading. They will tell you that in random forest, etc., you have feature importance coming in. Remember that those are very rough measures, global measures. Feature importance is a deep topic. And whenever you look at feature importance, so for example, a given user, suppose a user is, a person is 25, right? The person does, like at that particular moment, what do you think is the risk of diabetes? What is more likely to cause it, right? There are multiple things. You know that the young people are active. They're on their toes always. So you'd probably advise them to be careful about their diet. Right? On the other hand, as people get older and older, their exercise level goes down, but their food habits remain more or less stable. So now you want to emphasize, well, they're not likely to suddenly start overeating, and assuming their food habits are reasonably modest, now you want to start emphasizing exercise, right? Because people become sedentary as youth fades away. So things like that, what you advise or what factors matter more is like asking that how much does Y change? It's something as that, you know, if Y is a function of X, how much Y changes for each of the individual predictors in a for a given value of the X vector, right? So it's a local feature because you're essentially comparing, roughly speaking, the partial derivatives in the local region, right? You're looking at the gradients locally, gradient of Y with respect to each of these features locally. So this is getting a little mathsy, forget about that. But just remember that while people extol the virtues of feature importance in random forest and these models, take it with a grain of salt. Huh? Feature importance is more nuanced. Those of you, I noticed some of you are here after having done my boot camp last November, December. So you would remember that we devoted an entire day to the nuances and nuances of feature importance. And it also goes to the heart of something we are trying to do these days, recover interpretability of black box models. So, but anyway, this last part, by the way, is out of scope. So if you, I just gave you a teaser for things to come later on. If you didn't get the whole thing of it, don't worry at all. The only thing you should take back is the feature importance is there in a very rough way in random forest. Random forest is a complicated model. It is built out of you need to line up at least 4 ducks in a row. You need to use the concept of learners, ensemble of learners. Those learners should be weak learners. You make them weak by giving them a random projection of the data, right? A random data projected to a subspace of the feature space. You give each bootstrap sample. Then finally you aggregate the results. All these things are efforts to make sure that the trees or the learners are decorrelated, right? That's what you do. Now, one remarkable fact about random forest and a dirty little secret is, I said that number of features should be less than the square root of p. Now, here's the dirty little secret. Quite often, if you create a forest in which each tree is given only randomly one of the features, those are called stump trees, right? Stumps, a forest of stumps, no branches. Right? It performs remarkably well. Quite often, it performs as well as a more complex tree. Are we together? Right? So that is it. So that is random forest. What it addresses is this tendency in decision trees to fit data hard, to go and overfit to data. Decision trees always had the problem of overfitting. People did all sorts of clever pruning algorithms. And then came random forest. And then random forest created quite a tremendous debate in the community. People asked that machine learning used to be not just about making predictions, but about interpretability or providing some inference about what happened. Why is it happening? You lost that, you lost interpretability. Was the sacrifice okay? Today, we of course say that it is on a case-by-case basis. Right? Sometimes where only performance matters, you want the best model that you can build. So for example, if you want a self-driven car, you just want it to perform well and keep you safe and keep the other people on the road safe, right? Prevent accidents. You probably are not too concerned on what the interpretability of its decisions are. You just wanted to make the right decision, right? But on the other hand, in many other situations, for example, if you're trying to give a job based on algorithms and how people performed on a test, you want to make sure that the models are highly interpretable. You're not willing to take a black box that says, like an oracle, that, all right, this guy is better than that guy. So take this guy, don't hire that guy. Because there, interpretability of paramount importance, because there may be biases. If the data is biased, your machine learning algorithm will be biased. And a black box model, you will not know easily that there is a bias in your predictions also, because there was a very subtle bias in the data. In fact, companies have been sued for doing this. In US, you can get sued because we have the protected classes. You need to guarantee that you don't discriminate against the protected classes, race, gender, age, disability, and so forth, right? And so in the history of this is, without taking names, there was a company, a big company that was sued because it could be demonstrated that it was discriminating against the protected classes. They claim they're not deliberately doing it. They're feeding all the data they have into the algorithm, and the algorithms are blind and impartial, and so they are making predictions, therefore it is right. The judge did not quite agree. He says, no, it doesn't matter. The fact of the matter is there's evidence that your process is creating discrimination, is doing discriminatory hiring. Therefore, the circumstances of how you produce that doesn't matter. You're responsible for the wrong decisions. Right? They lost the case, and they had to pay a lot of huge penalty. So obviously in these situations, now you ask why it happened. It had to do with the fact that the data had inherent bias. The algorithmic training had bias, therefore. All of those things creep in. So there are situations where you can use black box models. There are situations where you cannot. And nowadays we are entering a world in which we are saying, well, we cannot but help use this very complicated black box models, right? Deep neural networks and so forth. But we want interpretability nonetheless. And so we are trying to create a whole new wave of body of research and tooling and stuff to restore some semblance of interpretability and explainability on top of black box models. So that's a very promising areas. Those of you who did the boot camp with me will remember some of it. And in the next boot camp, which is in deep learning, it will become a topic of paramount importance. Also a very hot topic today. So with those words, I will end now. Any questions, guys, on Random Forest before we close the session today?
Yes, sir. So in random forest, every tree is decision tree, right, sir?
It's a decision tree, yes.
Asif, is there a recommended sample size to do random forest?
Generally, it will do the right thing internally. It will look at your training data set size and it will pick a sample size. The basic rules of sample size is, you try to take a reasonably big sample, but you make sure that you don't take the whole set itself. Right? And, suppose you have 10,000 points and what's a square root of 100? So long as you're taking more than 100 points or so in a sample, it's good. It's a good sample.
How does random forest deal with high correlation between features?
It is actually very good. Let's say that the features X1 and X2 are highly correlated, right? The beautiful thing is one tree will get only X1, another tree will get X2. So you don't have the problems that you have, the pathologies that you have in linear models.
But doesn't it overcount the effect?
So what happens is that the beautiful thing happens is that when you ask for the importance, it will ascribe equal importance to X1 and X2, because some trees will be using X1, some will be using X2.
Okay.
That's how it is. So the problem of multi-collinearity, therefore, is moot when it comes to random forest. That was one of the big reasons people, when random forest came in, they were a runaway success. Every bit.
As if we lost you.
was using it. You go to Kaggle and use trees, boosting. You hear of all this cat boost, XG boost, and so on and so forth. And we'll talk about boosting the next time, next Monday. Remember,
I'm not sure if everyone heard a little bit of gap of what Asif was saying, or it was just me only.
guys,
No, it was for everyone.
Yeah, audio was dropped, I think.
We lost you in between, Asif.
Oh my goodness. Okay, so I'll say that again. What I was saying is that a lot of the if you go to Kaggle and you look at the winning entries for tabular data competitions, wherever data is tabular data, not image or sound or text, but the simple tables of data, you will often find that the winners are in the leaderboard. You'll often find entries of teams that are using one of the ensemble methods. They're using random forest or gradient boosting, this cat boost, XG boost, whatnot. They'll be using things like that. Very, very often you'll see them. You'll see at least some entries in the leaderboard coming from this. So this is a very popular algorithm. Obviously, like with every algorithm, people do get carried away. There are people who solve every single problem using a random forest. Right? So that's that. Actually, it reminds me of something very interesting. My good friend, Dilip, who presented on quantum computing yesterday, he and I used to have a joke. So he would say that we have to write code. So he would say, wait a minute. He would open the code editor, write int ij, and then he would say, now tell me what the problem is. Because he would always need the variables ij. It's like that. So nice, after all these years, when I think of random forest, it's like that. A lot of people swear by it. They'll say, okay, let me first instantiate a random forest, and then you tell me what the data is. And what should I fit to it? It's very effective. Right? And now we are entering the space of these powerful methods, very, very practical and very usable. And you use it a lot. Become good at it, guys. It will solve a lot of your problems. After this, we'll do boosting and its implementations, XG boost, cat boost, ADA boost, and all that. And then after that, we'll go to something, yet another very powerful idea called kernel machines or kernel methods. We'll do support vector machines and so on and so forth, right? So in this workshop, of course, we are moving fast. We're moving through rather powerful algorithms. Theory is done. Of this. Next time, remember, Wednesdays are for practice. We will do lab work in random forest. Lab work is an entirely different kettle of fish. You'll realize that lab is very easy. You just instantiate the random forest and fit it to data, right? But we'll learn to see its nuances. It's important to know some of the nuances involved, and we'll develop practice in that. Any questions, guys, before I end?
Just one question. This weak learner, right? Like in this case, you are showing them only weight or age, not everything. Subset of features, right?
Yes.
And they are doing prediction based on decision tree algorithm.
In random forest, yes. But in general, you don't have to. If you can create a bagging of anything you want, any other learners you want, you can make a bagging of, you could use logistic regression. So let's take this example. You want to do a linear regression. Remember, in linear regression, you have the fundamental problem that if there is multi-collinearity between the features, you're doomed. Right? You will start seeing explosion of variance. You start seeing pathologies. Your models are very unstable and they exhibit, variance inflations, like very sort of a slight change of the data will cause them to build entirely different models. One easy cure, just take an ensemble of linear regressors. You'll be and give them a random projection of features. You will realize that lo and behold, that problem is solved.
So, but all of these learners are using same algorithm, right, to learn?
Yes,
okay.
that is so. But now I'll teach, now the next thing I'll mention, actually, you sort of anticipated where I was going. You will ask this question, why can I not mix a few decision trees, a few linear regressors, Yeah, things like that, different algorithms. Why can I not do that? If I'm doing regressions, I can mix 20 different algorithms and instances of them. And likewise for classifiers, I can take a whole bag of classifiers, different kinds of classifiers, and do it. So yes, you can do that. When you do that and you create an ensemble of heterogeneous classifiers, you actually get very, very powerful prediction machines. In fact, that is one of my own dirty little secrets. In fact, hardly a secret, it's an open secret, because I keep insisting that everybody should do that. Never solve a problem with one algorithm. Use every good collection of algorithms and lots of instances of learners from each of the algorithms. Do the same process. Instead of trees, replace it with those with a heterogeneous bag of learners from
I see.
of different algorithms. And when you do that, it is surprising how much efficiency you get, because the weakness of one algorithm is made up by the strength of the other algorithm, and so forth. And you get very good thing. So bagging is one. We can do boosting. And the third thing is stacking.
I see.
Stacking is something that I find very, very useful. I'll stack predictions from different machines, right? Different learners. And then put a learner that learns from the predictions of the different learners. That is stacking. We'll gradually come to that. I don't know whether we'll do stacking in the practical methods, but we'll certainly do it in the boot camps.
I see. So here in random forest, when we say ensemble means ensemble of weak learners using decision tree. Okay, thanks.
Yeah, in random forest, it's safe because the word forest is yeah, forest of trees. It implies. All right, guys. So this is it. I will stop the recording.
I have one question.
Yeah, go ahead, Vijit.
So when you said heterogeneous classifiers or heterogeneous, algorithms, and they are like the example you gave, right? So the 100 features, and then you have, let's say, 10 learners or 100 learners, like that, getting 10. So they are, so you distribute those algorithms like equally among the learners. So let's say there are 10 learners and you're using 5, so 2 of the learners will use.
I mean, generally what happens is, in those areas, my experiences, and this is the experience. See, this is where, just like each artist has his own style, each data scientist will have his own rules of thumb and their own experience. My experience is I don't try to be very clever there. I just take a bag of learners and run with it, different heterogeneous learners, and run with it. I'll throw the same number of learners, but I'll make they all are doing their own random projections.
Okay.